Good morning, class. We are looking at statistics practice test number 5, module number 5, covering chapters 10, 11, and 12. Here's chapter 12, analysis of variance, or short, ANOVA. One-way analysis of variance, or ANOVA, is used for tests of hypotheses that 3 or more populations have a means that are all equal, as in H0, mu sub 1 equals mu sub 2 equals mu sub 3. So when we have more than 2, by analyzing sample variances, one-way analysis of variance is used with data categorized with one factor or treatment. So there is one characteristic used to separate the sample data into the different categories. The populations have the same variance, sigma squared or standard deviation sigma. And it uses the F test. In the F test for analysis of variance or ANOVA, 2 different estimates of the population variance are made. The first estimate is called the between group variance, and it involves finding the variance of the means. The mean of the first, the mean of the second, mean of the third, and so on. The second estimate, the within group variance, is made by computing the variance using all data, the entire data, and is not affected by differences in the means. It helps answer, are the group averages different just by chance, or is there real evidence of a difference? Instead of comparing groups one by one, like using many t-tests, ANOVA does it all at once using variances. In other words, you can just go with 2 of them and you can use the 2 tests. The first one and the second one, the first one and third one, the second one and the third one, so many different t-tests. Instead, we use one analysis of variance. If there is no difference in the means, the between group variance will be approximately equal to the within group variance, and the F-test value will be close to 1. Do not reject the null hypothesis. If the means differ significantly, the between group variance will be much larger than the within group variance. The F-test will be significantly greater than 1. Reject the null hypothesis. So that's how we figure it out. And as you recall, that's the F-test, which is skewed to the right, and we use a right-tailed test. The ANOVA test is right-tailed because only large values of the test statistic cause us to reject equality of the population means. Other statistical tests, such as Sheffield test and Tukey test, are used to find where the difference exists. If there's no difference, so be it. If there's a difference, where does it exist? Although the t-test is commonly used to compare 2 means, it should not be used to compare 3 or more. So more than 2, you go with the analysis of variance. Weights in kilograms of cypress trees were obtained from trees planted in a sandy and dry area. They were given different treatments as indicated. So no treatment, fertilizer, irrigation, fertilizer, and irrigation. Fill up the table below and use a 0.05 significance level to test the claim that the 4 treatments, 1, 2, 3, 4 treatments categories or factors yield cypress trees with the same mean weight. So what do we have? We have more than 2, therefore we go with the ANOVA. If there were only two of them, we go with the t-test. So what is the process? Again, this is not done by hand. I want to show you how it's done by hand if we want to do that. So we're going to discuss this table in a moment. We are going to fill this up. And to fill this up, here's what we get started with. Again, remember we have 1, 2, 3, 4 factors or groups or treatments. So we want to write n sub I. That means we want to write the n for them, which means 1, 2, 3, 4, 5. We picked 5 subjects, 5 objects. It so happened that N1 is 5, the rest of them is the same thing. So we're going to look at the first one. So N1 is 5. And these are the formulas that we are going to need. We're going to go over them in the next page as we go through them. But for now, N sub I, that means the first group N1 is 1, 2, 3, 4, 5. The next one, summation of x sub I. Remember, x represents each piece of data. X bar is the mean. So summation of x sub I. For the first group, add them up. Add these 5 numbers, 0.24, 1.69, 1.23, 0.99, and 1.80, and it's 595. The next thing we need is the average. X sub I bar is summation of x sub I over n. In other words, add them up, divide by size. We've already added them up, so 595 divided by 5. So that's how you get x1 bar. X1 bar. We are looking at this group. As we show for work for the first group, the rest of them repeat in the same manner. Sum of squares has this formula, everybody. Sum of squares, let's just do this. Means this. SS, sum of squares, equals summation of x sub I minus x bar sum k quantity squared. So for the first group, means 0.24 minus 1.19 quantity squared plus 1.69 minus 1.19 quantity squared, and the rest of it. So it means the following. The first number in the first group, see, we are looking at the sum of squares for the first group, 0.24 minus 1.19. That's the meaning of x sub I minus x bar, x sub k bar. So 0.24 minus 1.19 squared. 1.69 minus 1.19 squared. 1.23 minus 1.19 squared. 0.99 minus 1.19 squared. And the last number is 1.8 minus 1.19 squared. And it doesn't matter in what order, because when you square it becomes positive. Add them up. That is called the sum of squared. And that happened to be 1.5662 for this case. Variance for the group, just we use the formula. Remember, a squared is summation of x minus x bar quantity squared over n minus 1. Now, because we want for the first group, so we are using the variance for a sample, okay? And divided by n minus 1. We get 0.39155. Now, this one, the numerator is already here. N is 5, so 5 minus 1. In other words, divide this number by 5 minus 1 or 4. I'm not going to show the rest of them, but just for the sake of argument, 1, 2, 3, 4, 5, everybody can see this is 5, this is 5, this is 5, and we can see the rest of them in the same manner. So it does take a little bit of a time to do it by hand, but now you know how it's done. A quick recap. N1 is the size, sum, add them up, average, add them up, divide by size, sum of squares, each one, subtract the mean from it and square it and add them up, and then divide by n minus 1 becomes the variance for this group. Now, what do we do here? How do we use that? All right. There are some calculations that they need to be done, and we're going to go through them. So remember, we did this. X bar has this formula, S squared has this formula. We did this. So this is done from the previous page and put here. Now we're going to find the mean for the entire data. That's why they call it X sub GM bar. So that means what? Add this number to this, add all of those, plus those, plus those, plus those, and divide by 1, 2, 3, 4 times 5, divide by 20. In other words, find the mean of the entire data. So that is the grand mean, they call it. Now, we could also add up the means here and divide by 4 groups. And they will give you exactly the same answer because we found the mean for this group you can add. So you can calculate the mean for this group and it works out in the same manner. So X sub GM bar, so the grand mean. If one of the formulas in the previous page, SSB, the sum of squares in between, the sum of squares in between that is going to go there. N sub I times this quantity squared. For example, here. So N sub I happen to be 5 for each one. So they may be different. So for example, N1 is 5, N2 is also 5, but doesn't have to be. So for this one is 5 times 1.19 minus 1.0935 quantity squared plus, again, 5 because it happened to be 5. The average is 0.884 minus the grand average quantity squared plus 5 times the average is 1.194 for this group minus the grand one quantity squared. The same thing for the last one. That's how you get this. And that's 0.317295, and it goes right here. Now, as far as the degrees of freedom, K minus 1, you have 1, 2, 3, 4 categories, everybody. Okay. We have 4 categories. So we have 4 minus 1 here, 3, n minus k, total of 4 times 5, minus k, 4 categories, 20 minus 4 is 16. So we put 3 here, 16 here, we add them up, and we get 19 here, capital N minus 1. In other words, for the total, what is the size? There are 20 pieces of data, N minus 1. So that's how it works. The mean square would be the sum of a square divided by degrees of freedom. So this one by this one. and it goes in here. Now we want within, the sum of squares within. So that goes in here. Now the sum of square within n sub I minus 1, s sub I squared, or summation of x sub 1 minus x sub 1 quantity squared plus x sub 2 minus x sub 2 bar quantity squared, and so forth. That's the within. And so n sub I minus 1. For example, for the first group, n sub I minus 1. All of them, n sub I minus 1 is 5 minus 1 because they happen to be this. So that's 4. S sub I squared. Well, so in this case, 4 times this number. Okay. In this case, again, 4 happen to be 4 times this number. In this case, again, 4 times this number. In this case, 4 times this number, and add them up. Okay. Because it's been already calculated, that's the fastest and easiest way to calculate. And we end up with the following number when you put them up. And so this number goes in here. And this is the total. I mean, after you calculate, just add them up. This is SS, the sum of squares in between, the sum of square within, and this is the sum of square total. Add the two. Now you divide this one by this one according to this formula, and you put it here. So SS within over n minus k. So we have this number divided by this number, or you can say summation of S sub I squared divided by k. And gives you the same thing. In other words, you can take the average of those. If you take the average of those, that works out the same. 0.271373 and goes in here. So these are some calculations that are a little bit tedious. They do take some time, everybody. Now, the F has a formula, MSP over MSW, okay? So the ratio of these two numbers is the F we are looking for, the F test, and we put it here. So all of this calculation, of course, is normally done by hand. I want you to know that, everybody. But I wanted you to be exposed to that. So having said that, now that we have done this, now we want to do the test of hypothesis. So we are just putting the information, and this is given to you from Excel. Okay, so this table is given to you from Excel. We are going to do the test of hypothesis. There are 1, 2, 3, 4 groups. So H0, mu1 equals mu2 equals mu3 equals mu4. That's the claim. At least one of them is different. That's H1, and it makes it right tail test. Of course, we've run this test and we have the table. So we need the test statistic. This is FTS. Test statistic is 0.389741. And again, we have shown how to arrive at it, right? We've already done that. The ratio of these two. Now, we can look at the critical value. And the way you find the critical value using the F table or technology for that. Find the critical value number of groups factors. So k is 4, degrees of freedom is k minus 1 over 3. Total of 20, 20 minus 4, 16. That's the degrees of the denominator. And alpha is 0.05, and f has this value from the table or even technology. And again, we can see it here. Now let's do the drawing. The graph is skewed to the right. This alpha area is 0.05. This critical value is 3.23887. The test statistic is way smaller than that, somewhere here. It puts us way into the non-rejection region. By the way, the p-value would be the area to the right of that, okay? Here's the p-value in case. The p-value would be this area, just so you know, in any event. So it's way into the non-rejection region. And the p-value also is indicated here, which is way larger than alpha. So whether we look at the two numbers, traditional method, or two areas, alpha versus the p-value, we get to the same result, fail to reject H0. So what does it mean? Well, if we are not rejecting H0, that means we are not rejecting the claim. The claim becomes true. And now we write, there is sufficient evidence to support the claim that 4 population means are all the same. We conclude that the 4 treatments, those are the treatments, do result in cypress trees with the same weight. So that's analysis of variance, because we had more than 2 groups. Given the readability scores summarized in the following table and a significance level of alpha of 0.05, use technology to test the claim that the 3 samples come from populations with means that are not all the same. Notice that we are dealing with more than 2. So 1, 2, 3. So the very first thing we want to just do is let's just make up this table. N happen to be the same. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. N is 12. It happened to be the same for each one. Then we have Clancy, Rowling, Tolstoy. So to find the X bar, okay, let me just write the formulas again, reminding you. For the X bar, summation of X over N. So for example, for Clancy, you add those and you divide by 12. And of course, S would be the square root of X minus X bar quantity square over N minus. So you calculate those for each case. So those are the values that you can calculate. Now, you put that into some sort of a technology, for example, Excel, and you run that, and it gives you the table similar to what we saw there, right? Now we can write the test of hypothesis. Step 1, H0, mu1 equals mu2 equals mu3. H1, at least one of them is different, makes it right till test, and that's a claim because it said are not all the same. Do you see that? So the claim goes to H1. So we go with the test statistic. Okay. Clearly, this is your test statistic. 9.4695. F is equal to that. Then we want the critical value. The critical value is given there. That's FCV, that's FTS. We want to distinguish between the two. And we should recognize the degrees of freedom at 2 and 33. Okay, there are three groups. 3 minus 1 is 2. And n minus k, 36 minus 3, 33. So those are the degrees of freedom. You can look up the table or just right here. You have the critical value. And to understand the result, you put that into a graph. And when you put it into a graph, the critical value of 3.2849 is here. The test statistic is way into the rejection region. So if you compare the two numbers, obviously it's way into the rejection region and the result is reject H0. If you want to compare the p-value, the p-value means area to the right of test statistic, which is given here. So you can go with the p-value less than alpha 0.05, this number, or if you want to stop at the third one, 0 becomes 1. And no matter what, reject H0, which means if you're rejecting H0, you're accepting H1, claim becomes true. And you write, there is sufficient evidence to support the claim that the three population means are not all the same. We conclude that those books have readability levels that are not all the same. Now, if we were to use a TI calculator, one-way ANOVA, first clear list L1, L2, so and so forth. In this case, 1, 2, 3, L1, L2, L3. And then you do ANOVA. And so when you clear in L1, you put the first group 58.2, 73.4, and so forth. In L2, you put the second group 85.3, 84.3, and so forth. The last one, Tolstoy 69.4, 64.2, and so forth. So first you have the list. Then you run the ANOVA. And when you do that, it gives you this. And you see the arrow, you go down and you put more. Now, what do you find there? Take a look. These two are these two values. F 9.469 and so forth. That's your test statistic. And it gives you the p-value. Okay. So pretty much you're ready to make your decision. The p-value pretty much, and remember, it's 5.621 times 10 to the power of -4. Remember the meaning of it. What else it gives you, just in case? SS and MS for the between. SS and MS for the within also is here. So it gives you pretty much everything that has been calculated there, with the exception of the critical value. It doesn't give you the critical value.